Okay, hello everyone, and welcome to this webinar, which is titled 10 Years of Progress in Modeling Predictions, Decision Support, and Coastal Resilience Since Hurricane Katrina. My name is Dan Barry. I work in NOAA's Climate Program Office, and I will be the host of this webinar. This is a somber anniversary to observe as we recall the significant loss of life and property that occurred 10 years ago when Hurricane Katrina made landfall. NOAA staff members are motivated by such events to improve the nation's ability to prepare for and cope with the effects of hurricanes. This webinar is intended to share with you some of NOAA's scientific and other work related to hurricanes. Over the past 10 years, we've seen significant progress in our ability to accurately forecast hurricane activity on timescales from hours to months in advance. The scientific community has worked to increase our understanding of hurricane behavior, including the physics and dynamics of these storms, as well as how hurricanes may respond to a changing climate. NOAA has been engaged with partners in efforts to advance computer model simulations of hurricanes, which provide foundational information for forecasting efforts. NOAA has also focused on improving hurricane-related information and products disseminated to the public and has worked to increase the resilience of coastal communities and marine ecosystems impacted by hurricanes. This work to understand and prepare for hurricanes takes place in the context of broader hurricane-related efforts in other federal agencies, universities, the private sector, and other institutions. During this webinar, we're going to see 9 presentations from NOAA personnel covering the wide range of NOAA's work on hurricanes, including forecasting, long-range outlooks, coastal resilience efforts, and other topics. As a point of logistics, if you have any questions for any of the speakers, please send me, the host, a chat message via WebEx with your question typed out, and I'll pose the question to the speaker if we have time available. Our first speaker today is Rick Knabb. Dr. Knabb is director of NOAA's National Hurricane Center in Miami, Florida, which works closely with emergency managers, media partners, and the international community as the center provides new products and services. Rick, are you on the line?
I am. Good afternoon.
Hi, Rick. So I'm going to transfer control over to your computer right now. You're now the presenter, so if you just share your desktop.
Okay, can you see my title slide, A Decade of Changes Since Katrina?
Yeah, it looks great, Rick. So whenever you're ready, go ahead.
Okay, thank you. And good afternoon, everyone. I'm Rick Knabb, director at the National Hurricane Center. I'm heading into my 12th season at the National Hurricane Center, 4th as director, but the first 8 of my years here, from 2001 to 2008, were as a science and operations officer and then a hurricane specialist. And the first season that I held a senior hurricane specialist position was 2005. And I'm told by my colleagues that I experienced a career's worth of activity in one season, Katrina included. And if you don't remember what the track map looked like for 2005, it was certainly not just above average, but above normal. And another reason I show you this map is because I'm not just going to refer to Katrina, but some of the other events of the past 10 years that have contributed along with Katrina to some of the changes that we have been making to our products and services and that we are planning to make. The track for Katrina itself, as you may not remember, went right over the National Hurricane Center. It made landfall as a Category 1 hurricane right on the Broward, Miami-Dade County line, and the eye went right over NHC. And of course, we did have some impacts both to structures and people with some loss of life here in South Florida, but of course the really huge impacts, the scale of which don't see very often, is after it made its way into the Gulf of Mexico and impacted the northern Gulf Coast. So one of the changes that has happened over the last 10 years is continued improvements in the accuracy of track forecasts. If you look at depiction of what would the forecast cone look like from the National Hurricane Center for one of the advisories when Katrina was in the southeast Gulf, what would it look like in 2015, given our present day forecast accuracy as compared to what the cone looked like in 2005. And of course, this cone is somewhat arbitrary in terms of its size, but what it does represent, generally speaking, is the probable location of the center of the cyclone over the next, in this case, 3 days. And because of the continued improvements in our track forecasting ability, owing largely to continued enhancements to computer models, the cone would be smaller today. Of course, that's good news because that's reflecting more accurate forecasts, but it does bring forth a new and interesting challenge, which is that the more narrow the cone gets, because hurricanes aren't getting any smaller, the impacts that you can experience outside the cone, that's going to happen more often, because even if the center stays within the cone, the impacts can extend outside of it. And so more and more we are having to emphasize the hazards and not the track forecast or the cone. It's becoming even less useful than it already was 10 years ago for conveying where the impacts are going to be. But it certainly is good news in terms of our track forecast getting better. And if you look past the last 25 years or so, including the last decade, going back to 2005, our Atlantic Basin track forecast errors from the Hurricane Center, our official forecasts, were almost 60 nautical miles at 24 hours a decade ago. And then going back to last year, it's getting close to 40 nautical miles. So we're continuing that downward trend in the track forecast at all lead times. And by the way, if you look back to around the time of Katrina, that was very early in the game in terms of us offering five-day forecasts. And we've had another decade of those under our belts. And one thing we're headed toward in the future, we're already internally testing 6- and 7-day forecasts. That's not going to be made public this year, even experimentally, but over the next few years, we'll continue to test that. And it's just a matter of time before we extend the forecast time horizon beyond the current 5 days. And by the way, as you may know, intensity forecasts generally still have not improved, and that is one of our biggest forecast improvement needs, especially rapid intensification, especially near the coast. Now, go back to the time of Katrina. At that time, one of our operational products today was experimental, our wind speed probabilities that leverage our knowledge of our forecast errors. And this was an example of what the experimental wind speed probability products from the Hurricane Center looked like during Katrina. And it was after 2005 in 06 when they became operational, but they were already being posted on our website experimentally during Katrina to take some of the focus off of the exact track forecast and off the cone and be more hazard specific and location specific, because on this map you pick a point, whether it's on the coast or farther inland, and it tells you what the chances over the next 5 days of experiencing on the left winds of tropical storm force or on the right winds of hurricane force. And the area that we thought had the highest chance of receiving hurricane force winds for Katrina when it was centered in the southeast Gulf, it extended over a fairly large area, and we were able to convey with this graphic that it wasn't just going to be a problem for where the center went. We had a risk of hurricane force winds at the coast and inland over a fairly large area. So this accounts for the uncertainty and was something that went through the Joint Hurricane Testbed, which is our program for making the transition from research to operations. And this went through the JHT, and we've had another decade of JHT projects since then. So the JHT, since Katrina, has continued to contribute, but it was doing so around the time of Katrina, and we've continued to use this operational product to this day. Now, the other thing that I think about when I think of Katrina is I immediately also think of Charley, because after 04 and 05, and especially after Katrina, and by the way, I had to issue, I co-authored the official Hurricane Center report on Katrina, also did some of the forecasts as a hurricane specialist in operations, but after we issued the report on Katrina, when we determined, based on post-event analysis and all kinds of aircraft data in the Gulf of Mexico, Katrina being one of the most heavily sampled cyclones over the Gulf, we determined that it was Category 3 in terms of its strength when it came ashore in the northern Gulf Coast. And a lot of folks were then comparing the impacts of Katrina to the impacts of Charley. But because Katrina was so much larger, the storm surge was so much worse, and because of where it made landfall. And that really got the conversation going that led us in the 09 and 2010 timeframe to explicitly call the scale the Saffir-Simpson Hurricane Wind Scale, because it's not just the wind speed that determines the storm surge you get, and the category does not tell the whole story. It tells you what the wind hazard could be overall, but it does not tell you what the storm surge hazard is going to be. So this comparison really got the conversation going that it's much more than just the category, and got the conversation about size going in a very important way, because if you think about what's happened in the decade since Katrina, Wilma, Category 3, the last major hurricane to hit the U.S., and the last hurricane hit Florida. But since that major hurricane, we've had major impacts without major hurricanes. Ike, Category 2 in Texas in 2008. Hurricane Irene, that was not a major hurricane when it hit North Carolina, and it's known for the flooding that it caused in the Northeast. Isaac was Category 1 when it hit Louisiana, was a tropical storm when it caused the flooding you see in the upper right in Florida. And Sandy was not a major hurricane when it hit the U.S., but we know all the impacts that it caused. So clearly, the focus on the category is not something we want to continue into the future, and so we have focused on the hazards. And that has been bolstered by the stats that we've done, published this study last year that includes Katrina and many other systems in terms of what's causing the fatalities. It's mostly storm surge, and a lot of it is rainfall causing inland flooding and other water-related causes of fatalities. Wind is only causing about 1 in 10 fatalities over the last half century. So we are focusing on products and warnings and services, including decision support for evacuations, that focus on the individual hazards, primarily storm surge, which has led us to this new product. This is a prototype of our potential storm surge flooding map that shows you how far inland from the coast the storm surge could go and how high above the ground the storm surge flooding could get. That's a significant change as well since Katrina, that we have started to communicate storm surge in terms of how high above the ground, not above some reference level. And last year, this is the culmination, I think, over the last decade. Last year, on the left, you see the graphic that we disseminated during Hurricane Arthur, the first time our potential storm surge flooding map was experimentally disseminated to the public for Hurricane Arthur. And on the right is a graphic that we would issue this year as a prototype of storm surge watch warning. It's not an actual warning this year, but by 2017, we anticipate that it will. So over the last decade, not just because of Katrina, but because of a lot of other storms, we have improved our forecast accuracy in terms of track, and I think we have changed the game in terms of how we communicate the primary hazard that we'll remember Katrina for, and that's storm surge. And looking forward, I hope we can continue to focus more on the individual hazards and give a little more focus to the inland flooding hazard. So those are the highlights of the last decade from Katrina, and I thank you for listening, and I'll be hanging on for any questions.
Hi, Rick. That's great. Thank you so much for the presentation. To everyone who's attending virtually, I'll remind you that you should send me a question by chat. So send a chat message to the host if you have a question, and then I can pose it to Rick. So we'll wait a little bit while people type away.
Just do you directly?
Yeah, sure. And Seth, feel free to ask in the mic. Yeah.
Rick, if you could, this is Seth Borenstein at the Associated Press. You were talking about the storm surge sort of warning as of 2017. What about the concept of a storm surge version of the Saffir-Simpson scale? How far do you, would that be in itself useful? Why or why not? And what's being done there?
Yeah, thank you for the question. A great question, one that we have grappled with internally and that has come up many times. We have gravitated toward, instead of trying to come up with another scale that would not be able to capture the wind, the storm surge, the inland flooding, the tornado hazards, and every other hazard, there's no one scale that will capture all of the hazards. And so what we've done, instead of coming up with a storm surge scale that people would have to translate into what it means to them, what you see on the screen here with that graphic on the left and the prototype that I've got on the screen here from South Carolina, there's no scale. It's simply a direct conveying of how high the flooding could get due to storm surge at whatever location you are concerned with. So we think rather than scales, we need to be connecting with people directly on each individual hazard, and we're doing that with storm surge in terms of feet above ground level. And we will deal with the wind hazard in terms of miles per hour. We will deal with the amount of rainfall and inland flooding in its own right, and the tornado hazard in its own right.
And forgive me, I came in a little late. Louis earlier said there was about I believe a 20%, 10 to 20% improvement in intensity forecasting accuracy, and I thought I heard you say there hasn't been. Can you sort of reconcile that to me? For me?
Sure. Now, what we do in order to measure our accuracy in terms of intensity forecasting is we look at our official forecasts and we compare that with what the actual intensity was. And if you look over the last couple of years, by the raw numbers, the average errors have come down a little bit, but you have to look at that in the context of how inherently difficult the forecasts have been. And so over the last 2 to 3 years, when we haven't had as many major hurricanes, we haven't had as many rapidly intensifying systems, we don't feel comfortable yet saying that we are definitely on a trend toward improving our intensity forecast, because as soon as we have a year where there are a lot of majors, a lot of rapid intensifiers, the errors could go dramatically back up. So you have to look at the raw errors, but relative to what the difficulty of the forecasts were and what we call forecast skill. And we don't see a measurable improvement in our intensity forecast skill yet, especially just looking over 2 or 3 years. We need to see a longer trend, and we need to get back to a year with a lot of stronger storms to gauge if we've really improved.
Great. Thanks for the question, Steph. So, Rick, there's one question from the chat room, and this individual is asking what land elevation data is being used to determine the above ground level values that you mentioned.
Yeah, we're using some high-res digital elevation model data, and we're able to take what is relatively coarse storm surge model output and post-process it in a GIS environment in order to give you the granularity that you see in the depiction here. Now, it's down to the community level, not down to the house level. But we're using the highest resolution digital elevation model data, which varies in terms of its resolution depending on what location you're talking about. But it's DEM data in a post-processing environment in a GIS system using, by the way, a large collection of storm surge model outputs using a variety of tracks and intensity. So this graphic is telling you what the potential is at any given point on the map, not what will happen. It's got uncertainty already built into it.
Okay, great. Thanks a lot, Rick. I think we should move on to the next speaker now to stay on time, but I really appreciate you presenting.
Okay, thank you.
Okay, the next presenter is Gerry Bell. I'm going to transfer control over to Gerry's computer. Dr. Bell is a meteorologist at NOAA's Climate Prediction Center. He's NOAA's lead seasonal hurricane forecaster and is also a specialist in monitoring, analyzing, and predicting global climate patterns and their impacts. Gerry, are you on the line?
Yes, I am. Do you see my screen?
Not yet. I think you still have to share your desktop. Either click the button or go to the share menu and then select my desktop.
Click share screen. Okay. How's that?
Looks good. Whenever you're ready, go ahead.
Okay. It's a pleasure today to talk about some of the features that make up NOAA's seasonal hurricane outlooks. There's a tremendous amount of science that goes into these outlooks, and the scale of the climate patterns and the wind patterns that we look at is far, far beyond that of a single hurricane or tropical storm. So it really puts these outlooks into a climate perspective on what is controlling the wind patterns and the wind shear and ocean temperatures over large scales for months at a time, rather than what is making us conditions conducive or unconducive in a particular storm environment. We've been issuing the seasonal Atlantic hurricane outlook since 1998. They're an official product of the Climate Prediction Center, but they're made in strong collaboration with hurricane specialists from the Hurricane Center, Hurricane Research Division, and we also issue outlooks for the Central Pacific region now, so I deal with the Central Pacific Hurricane Center. For this talk, I wanted to keep things kind of simple and just kind of focus on the outlook regions the regions that we make outlooks for, and then highlight some of the ingredients that we see that produce hurricanes, and then translate that information to the much larger scale, spatially and temporally, so that we can kind of see what goes into making the seasonal hurricane outlooks. These are the outlook regions. The Atlantic Basin, as I mentioned, we started issuing outlooks in 1998. And on the left shows a whole bunch of storm tracks over many, many years. And the key thing here is that yellow region. That's the main development region. That's where, if you're going to have an active season, that's where you're going to have a lot of storms, and that's where conditions will be very conducive. If it's going to be a low activity year like this year, conditions in the main development region will be very suppressive and will have little activity. So that main development region is really the core prediction region. Now, that region is also important because I've indicated a couple of main storm tracks that the storms take coming out of that area. One is a grouping of storms that head toward the Caribbean, through the Caribbean Sea, and up into the Gulf of Mexico. And fortunately for us, a lot of another track is the storms that recurve and off to the northeast before making landfall. But regardless, look where the main development region is and look where the United States is. We're at threat every single year from a potential hurricane. We're lucky when they don't strike, but we need to be prepared every hurricane season because we all know it only takes one. We also issue outlooks for the Central Pacific. That's a much less active region, but the interests in Hawaii are the primary concern there. And the third region we issue for is the Eastern North Pacific. That's a very intense hurricane formation region. Fortunately, most of those storms head westward and stay out to sea, but on average, maybe 3 or 4 storms a year will recurve back up to the northeast, impacting Mexico, Central America, or even into the Baja Peninsula. This is an example of the hurricane outlooks and the nature of the outlooks. Our outlooks are probabilistic, meaning that we indicate that there's certain likelihood of ranges of activity and overall season strength. And that's typical of a climate type of forecast. Nothing's 100%. We try to best give what we expect within probabilities. This is the forecast that we actually issued in late May. We'll be updating the August outlook on the Atlantic outlook on August 6th. But you see that the couple of key things that we indicate the likelihood of an above or below normal season, the overall season strength, and then we indicate the likely ranges of activity, named storms, hurricanes, major hurricanes, and so on. And we indicate those with a 70% probability of occurrence. So if we're doing things right, we should expect to get these ranges correct about 70% of the time. We don't expect them to be correct 100% of the time because that's simply not the nature of the forecast. Now, the outlooks are really an outlook for the overall hurricane season strength. They're not a landfall prediction, and they don't predict levels of activity for any particular region. And the reason is really quite simple. Where a storm strikes, how strong it is when it strikes, its exact track, and all those types of things, they depend on the weather patterns that are in place at the time the storm's approaching. And as Rick was showing, we really don't want to be predicting those features more than about 5 days in advance right now. Now, there's just to highlight a few key ingredients for a hurricane, and these most people are familiar with. The first is warm waters. Hurricanes like warm water. The warmer the water is, the potentially the stronger the hurricane can be. For the Atlantic, hurricanes and tropical storms typically also require a trigger. This trigger is often cloud systems or low-pressure systems moving westward from Africa. They're called African easterly waves. And it's this trigger that produces nearly all the tropical storms and hurricanes in that main development region. Now, whether the system intensifies or not depends on lots of things, but perhaps most crucially is the vertical wind shear. The vertical wind shear refers to how the wind speed and direction change as you go up to the atmosphere. And here I've indicated in this schematic winds out of the east at both lower and upper levels, And that means that the wind shear, or the change in wind speed and direction as you go up through the atmosphere, is very weak. This would be a classic wind pattern to really intensify a storm into a hurricane or major hurricane. This leads to the scientific basis for the seasonal hurricane outlooks, is that active or inactive seasons, they often result from a coherent set of conditions, such as I just mentioned. And those coherent sets of conditions are often strongly controlled by tropical climate patterns, which means they're not random. An active season typically is not a random coming together of warm water and weak shear, for example. So what this map shows is a set of conditions typically associated with an active hurricane season and decades. And when we see or predict these conditions, that would certainly be the basis for predicting an active season. But note the huge region over which these conditions exist. In this case, I've indicated warmer waters, weaker wind shear, more conducive winds coming from Africa, along with weaker trade winds, a stronger, wetter West African monsoon. This is a classic set of conditions that produce an active season. And again, key is that these conditions occur in this main development region, and they can really fire up a season. Opposite conditions produce much weaker hurricane seasons. Now, what's very fortunate for us is that this interrelated set of conditions has strong links to tropical climate patterns. And by monitoring, understanding, predicting those climate patterns, we can then oftentimes predict the set of conditions as you're seeing now, and thus oftentimes make an intelligent assessment of what the upcoming hurricane season will bring. There's two dominant climate factors that we look at, and predicting these climate factors is really the underlying basis for making the seasonal hurricane outlooks. One that you're all familiar with is the El Nino and La Nina cycle. And El Nino and La Nina primarily cause year-to-year changes in hurricane activity. This year we have an El Nino. It's a significant El Nino. In May we predicted the season to be below normal. That's how these things kind of work. Just because I'm mentioning El Nino, that's at the bottom. El Nino refers to when it's warmer and wetter than average across the entire eastern half of the equatorial Pacific Ocean. This is a massive region, and this warm and wet conditions affect the wind patterns not only over the Pacific, but also over downstream over the Atlantic Basin as well. And what the El Nino winds do is they act to create stronger shear. That suppresses the hurricane season. In contrast, La Nina refers to when it's cooler and drier than average over the eastern half of the Pacific. The upper-level wind patterns associated with La Nina are such that they produce weaker shear, favoring more Atlantic hurricanes. Now, there's another, even more prominent pattern that we see, and it lasts for decades at a time. It's called the Atlantic Multi-Decadal Oscillation, or the AMO. This is a climate pattern that historically lasts for 25 to 40 years at a time. And it's important for hurricane activity because it creates that entire set of conditions that are either more favorable or less favorable for hurricanes. A typical climate patterns for an active hurricane era that we saw in the 1950s and 60s, and really since 1995, when we've been having so many active seasons, is the warm phase of the AMO. Warmer than average temperatures across the tropical Atlantic and at high latitudes, along with a stronger, wetter West African monsoon. This climate pattern produces active seasons. Opposite conditions, cooler ocean across the Atlantic, weaker, drier monsoon produce much less active seasons for decades at a time. And the most recent low activity era was, in fact, 1971 to 1994. So again, the outlooks are based primarily on predicting these climate patterns and their combined impacts during a given season. The outlooks also reflect current and predicted regional conditions such as the exact Atlantic Ocean temperatures, vertical wind shear, and so on. This shows an example of how prominent that AMO climate pattern is. The top, I'm just above my cursor, shows the average number of hurricanes in green that we saw during that low activity era, 1971 to 94. And the red bar shows the average number of hurricanes we saw during 95 to 2012. That's a 60% increase. We went from 5 hurricanes a season to 8. During those same periods, we saw the number of major hurricanes more than double. And if you look at what we classify as very active seasons, and those are the ones when you have high probability of multiple hurricane strikes, we had no very active seasons during that low activity era, and we've had 8 since 1995. Again, that's how prominent that AMO pattern is and how important it is as far as making the hurricane season predictions. Comparing the same period, if you look at hurricane landfalls, during the low activity era, we averaged a little over 1, whereas since 95, we've averaged almost 2, basically about a 50% increase. And that number is also seen in Atlantic Coast major hurricanes. This was a plot I got from Bill Gray many years ago. The plot on the left shows the number of major hurricanes striking the U.S. during 2 exceptionally low activity periods, but it spans 47 years. We had a couple of major hurricanes. On the right shows the major hurricanes threatening the U.S. during roughly the same number of seasons during high activity eras.
Hey, Gerry, sorry to interrupt, but please try to wrap up in the next. Oh, great, you're on the summary slide. Perfect.
Right. Sure, okay. So the underlying basis for the outlook is really predicting these strong climate patterns, and by doing that, we can often make an intelligent forecast for what the season brings. And since Katrina, we've seen advances in all aspects of the hurricane season outlooks, from monitoring and analysis to research and understanding of these climate patterns and their impacts. And perhaps one of the most important advances really has been in the development of climate models, not only in their sophistication, but also in their resolution. It's amazing what we're doing with these climate models now. And as a result, we've had significant increases in the outlook skills since 2008. So I'll finish there.
Great. Thanks a lot, Gerry. I think in the interest of staying on schedule, we'll have to move along to the next speaker. But if anybody does have a question, please do send it to me through the chat function. And if we have time left at the end of the webinar, and Gerry, if you're able to hang on until then, we maybe can come back and have a discussion. Is that all right?
Sure.
Okay, great. And thank you so much, Gerry, for presenting. Okay, the next speaker is Bob Atlas. Bob, are you on the line?
Yes, I am.
Okay, great. So Bob is the director of the Atlantic Oceanographic and Meteorological Laboratory. He's also a former NASA modeler and an Air Force forecaster. And Bob, your slides are up, and feel free to take it away whenever you're ready.
Okay, thank you. So NOAA's Hurricane Forecast Improvement Project provides the basis for NOAA and other agencies to coordinate hurricane research needed to improve significantly the model guidance for hurricane track, intensity, and storm surge forecasts. The overarching motivation for HFIP is to increase forecast accuracy, especially for the longer lead times, and especially during periods of rapid intensity change. And the rapid intensity changes are the most difficult part of the hurricane forecast. The goal here is to raise the confidence levels through increased accuracy, and these increased confidence levels then would help mitigate loss of life and damage from the storms. The specific goals of HFIP, which are very ambitious, are to reduce the forecast errors in track and intensity by 20% in 5 years and by 50% in 10 years, and also to increase the forecast period out to 7 days with an accuracy that was previously available at 5 days. One of the keys to success in HFIP has been partnerships, and initially we had several organizations in NOAA, in the Weather Service, and in the Office of Atmospheric Research that were doing hurricane research and interacting at least a little. But with HFIP, the interaction between all of these organizations, as well as researchers in other agencies, such as NASA and the Navy and NCAR, and many universities has increased tremendously. And what we have in HFIP is a close alignment of the research with operations. We have partnerships between the federal government and academia, and this has greatly increased the number of people working to address our priorities for improving hurricane prediction. Another key to the success in HFIP has been making operational models, and in particular the operational hurricane models, available to the entire research community through the Developmental Testbed Center. And in this way, research performed at other locations is more directly applicable to what we do in operations and more quickly transitioned into our operational forecasting. Other keys to the success in HFIP have been observational scientists working very closely with numerical modelers and the interaction between the research community and operations. And all of this has accelerated the development of NOAA's models, particularly NOAA's hurricane models. The current state-of-the-art for intensity forecasting is shown here for the National Hurricane Center, and this is showing that up until the start of HFIP, around 2008, that we had generally no improvement in intensity forecasts, at least being demonstrated by this metric. Since the start of HFIP, we've seen meaningful improvements in hurricane intensity prediction, but as Rick Knabb pointed out, the sample here is not long enough to be confident in this trend and also doesn't contain perhaps the hardest hurricanes to predict. A key aspect to the improvements that appear here are the rather remarkable improvements that have occurred with regard to NOAA's models, both its global model, known as the Global Forecast System, GFS, and its regional hurricane model, known as HWRF. These graphs are showing the skill of NOAA's Global Forecast System and the ECMWF model, green for NOAA, yellow for ECMWF, in the period 2006 to 2008 as we look from 1 to 7-day forecasts. And what you can see in this earlier period, that NOAA's models were not demonstrating skill relative to a baseline. ECMWF did have modest skill in this period. In 2012 and beyond, we've seen major improvements in our operational predictions with the global model for hurricane track. And what we can see is through 4 days, NOAA's model is comparable to and sometimes better than the ECMWF. At 5 days, both models are forecasting skill, with ECMWF a little better, and we're still need to increase the skill in the longer time ranges, 6 to 7 days. With regard to intensity forecast, this chart is showing the forecast error in knots, nautical miles per hour, wind speed, for the HWRF model. And what's shown here in black is the baseline skill level that was established at the start of HFIP, the 5-year goal for HFIP in intensity, and the 10-year goal for HFIP in intensity. The 2011 and 2012 versions of HWRF were less skillful than the baseline, but you can see a very substantial improvement from 2011 to 2012. Another substantial improvement in the 2013 version of HWRF, and now substantially better than the baseline, and then continued improvements with the 2014 and 2015 versions of HWRF. Each of these are from retrospective runs involving several years, 3 to 5 years of forecast model integrations. So we are seeing a definite improvement in intensity forecasts with the HWRF model. Another way in which we're improving HWRF is by extending it from a storm-centered domain, which can handle one hurricane or one tropical cyclone at a time, to a basin-scale version of the HWRF, which can handle multiple storms at the same time, and also take into account the interactions that occur between storms. And we're trending towards a more global version, as shown here, where many hurricanes can be handled at the same time, and we're bringing the resolution of these versions down to about 1 kilometer in the near future. One recent achievement in the area of data assimilation occurred with the assimilation of the NOAA P3 tail Doppler radar data for Hurricane Arthur. And this data was used to produce HWRF forecasts in real time, and HWRF was the first model to accurately predict that Hurricane Arthur would strike the Outer Banks in last year. And this year, we're increasing the observing systems on the P3, including now a Doppler wind LiDAR that will be able to measure wind profiles in the non-precipitating air and complement the tail Doppler radar data. Thank you.
Great, thanks a lot, Bob. There's a few minutes for questions. So again, for those participating virtually, please use the chat feature and send me a question, and I can pass it along to Bob. Any questions in the room here? Okay. Okay, so Bob, I'm not seeing any questions, but if any come up, sometimes people take a little while to type. We can maybe come back to it later. So thank you for your presentation.
You're welcome.
There is one question for Gerry Bell. Seth, if you'd like to ask it, let me just see if Gerry's on the line. Gerry, you still there?
Yeah.
Hi, Gerry. There's a question from Seth here in the room.
Hey, Gerry, it's Seth at AP. Just in terms of the AMO, forgive me because I haven't been keeping up, is there any indication of, how long this AMO, this warm one, will last, besides just climatology? What are the current measurements showing in terms of strength, or weakening?
Well, typically these periods last anywhere from 25 to 40 years historically. What we've seen really this year as most is that we're actually seeing colder waters in the tropical Atlantic and at high latitudes. So at least temporarily, we're seeing the cold phase of the AMO. We've been seeing that so far this year. But whether that's just a temporary blip or not, there's no way to really say at this time. As of last year, the waters in the tropical Atlantic were still above average. So I don't think there's a clear signal whether we're getting out of this warm phase of the AMO yet.
Has there been times in the past where you've seen similar cold blips during a warm AMO?
Sure, and you see warm blips during the cold AMO. You see, there's year-to-year fluctuations in the strength of this event just depending on the trade winds, El Nino, La Nina, things like that. So it's not just a steady overall warm with nothing to beat it. Typically the pattern is so strong that it dominates, but not every year.
Thank you.
Great. Thanks, Gerry.
Mm-hmm. Sure, thank you.
Next speaker is Steve Goodman. Dr. Goodman is the Senior Program Scientist for the GOES-R satellite program. He has research interests that include the global distribution and variability of thunderstorms, lightning, and precipitation physics, and the application of space-based remote sensing to improve the short-range forecasting of severe storms. Steve, are you on the line?
Yeah, I'm here.
Hi, Steve. So just, I've made you presenter, and if you could share your desktop with us, we'll be good to go.
Okay, are you good?
Yeah, looks good. Whenever you're ready.
All right, good afternoon. So what I'm going to talk about here briefly is our next generation geostationary satellite constellation that will be launching in 2016. This is a large departure from what we've had for the last 1 to 2 decades. And this new system will be 4 satellites replacing what we have over the Atlantic and Pacific and covering the continental U.S. And they will then replace each other. And that series will go for about the next 20 years. So this is what you'll have to work with. And I think you'll find it very exciting in terms of possibilities. So the capabilities of the new GOES-R satellite, we have 3 times greater spectral information, 4 times greater spatial resolution, and 5 times faster coverage for the high-impact weather phenomenon. We have a new measurement to map total lightning. That's not just the lightning that goes to ground, but the lightning in the cloud, which is more closely coupled to the dynamics and kinematics of the storms. And we also have some new advanced instruments for monitoring space weather, such as solar storms and solar flares. As I mentioned here, it'll help us with more timely information, more accurate information, and actionable information for improved hurricane track and intensity forecast, thunderstorm and tornado warning lead times, wildfires, dust storms, volcanic eruptions, and solar storms. And so I just wanted to give you an idea of the breadth of the societal benefits for the new constellation. Again, weather impacts on society. We have many disasters, of which the tropical cyclone hurricanes and their flood and wind impacts is just part of the societal impacts. They're quite intense. One other product that's not on this prior slide: tornadoes, hurricanes, floods, blizzards, lightning, volcano eruptions, fog, and so forth, is with the new capabilities in spectral information, we're able to do a better job of discriminating things like dust and aerosols. And here I just want to show you one example. I don't have it for an Atlantic developing tropical cyclone because we're not up in orbit yet. We've been using low Earth orbiting instruments, NASA research instruments, as proxies for the kinds of information we'll be able to get continuously from the vantage point of geostationary orbit. Here's an example, a day when we had not only severe storms in the southeast U.S., you can see we had a strong jet stream, and then here, in this image here, from an instrument called MODIS, it's a low Earth orbiting spectrometer, you can sort of make out what might be a feature related to dust, but what really comes out dramatically is when you use the additional spectral bands that we have on the satellite, you can really pull out the blowing dust, and then this is what it looked like on the ground here in Colorado. I wanted to give you a sense of scale. The current satellite looks like this. It's been fully assembled and it's undergoing testing until we launch next year. And it's quite large compared to, a typical person here. It's maybe school bus size. This up here is the new imager. The current imager we're flying is about the size of a say a dorm room refrigerator, and you can see here's the new imager, and it's quite a bit larger. It's about as tall as a person. And so as I point out here, we get about 60 times more information with the new imager than we have today because of the increased spatial, spectral, and temporal resolution. We have 16 different spectral bands in the visible, near-infrared, and thermal infrared to measure different geophysical properties. It will improve every product we have because it'll be more accurate and have the higher resolution, and that will benefit the tropical cyclone forecast, and I'll show you some examples here. You can see on the lower left here with our current imager on what goes 13, 14, and 15, currently on orbit, we only have 5 different spectral channels, and with our new imager, this is simulated imagery from a model, what it would look like. We'll have a lot more information on the individual storm, not only the storm, but also on its environment. Now, here's an example of what the data will look like, except this is really not as rapidly updating as we'll have. This is from the recently launched Japanese Himawari imager, which is observing typhoons in the West Pacific. It became operational July 7th NOAA's been working closely with the Japanese Meteorological Agency. Our vendor for this instrument has actually built 7 of them. 4 were purchased by NOAA, 2 by the Japanese Meteorological Agency, and 1 by the Korean Meteorological Agency. And there's a lot more detail. So we have spatially in the visible, as you see here, instead of 1 kilometer, spatial resolution will be 500 meters, which translates into, instead of about 3/4 of a mile spatial resolution, now down to about 1/3 of a mile. And that increased spatial resolution also will translate into looking at sea surface temperatures with higher resolution and being able to resolve temperature gradients. The forecasters don't necessarily find that this high resolution is something they know how to make use of today, but when the eye wall is not so well developed, the higher temporal resolution is helpful for center fixing, which is important information for the track and intensity forecast. Another thing we can do with this imagery, here's an example from Hurricane Sandy. We were running an experiment with our spare on-orbit GOES-14 satellite, which we happened to be able to run during the 5 days in October as Sandy came up the coast. And today, because of the lower spatial resolution and also the channels, on the left here is the type of wind barbs, wind vectors we get. We track the wind by taking different successive images and follow coherent cloud properties. And it would be maybe akin to if you throw a pebble in a pond and you watch those waves go out from the center, you can follow something coherent like that as it moves out. In the same way, we're able to follow these cloud patterns and also moisture features. And on the left is what we get today because we're only updating every 15 minutes. And from the Hurricane Sandy example, we're able to get many, many more wind vectors, which go into the global forecast models that were mentioned earlier. And we anticipate once we have an understanding of how we can make use of these, they may even be able to be assimilated, as Bob was describing, into the regional scale, like the hurricane forecast models, and also at high resolution. So we looked at this may have a fair amount of benefit to the end users. We also can calculate the individual cloud tops and look at how the winds are expanding outward or coming inward, and that should help us in diagnosing the characteristics of individual storms that are embedded within the hurricane rain bands and eye wall. Here's another example. This is Typhoon Dolphin off the northwest coast of Guam. This was taken from May of this year, again with the Himawari satellite. Now they take their imagery 2.5 minute refresh rate. The GOES-R will update every minute. So we'll have more frequent updates that will help us follow features a bit better. But this does have the higher spatial resolution than we have today, and you can see a lot of detail in these images. So back to these wind vectors, here's an example of these derived motion winds we can do, and you can see how these play a role in going into, say, a global forecast system to give us more information about the environment, where we can look at things like horizontal shear. We don't have a very high vertical resolution, but we're able to do wind height assignments much better today or in tomorrow than we can today. There's also a speed bias in today's estimates, but by being able to do more successive rapid images and get these wind vectors, we'll be able to reduce some of the speed bias. So overall, we expect improvements in the global model. Here's an example of what we might be able to do then at the regional scale. This is showing you an example of these wind barbs, the high density winds you get here. This is Hurricane Ike, and you can see from this experimental data that you get many, many of these wind barbs. But what I find most fascinating here is looking over here in the lower left in the intensity analysis. The red line shows you the observations. The control model is shown in dashed blue, and here with the rapid scan information in green. And what's interesting is here at the beginning part, during the period of rapid intensification, by having these what we call high density winds, we presumably will be able to do a better job picking up the initial stages of that rapid intensification with the high density or rapid refresh winds than we can today. The other thing that will be very interesting is the air mass. We call this the air mass RGB for trying to assign color guns, red, green, and blue, with the different spectral bands to the imagery. And what that allows the forecaster to see is different types of air masses, so moist air and dry air, for example, intruding. In this case, the blue is representing descending air from high up in the atmosphere, and it's bringing dry air into the storm, and it's a contributor to helping it weaken with time. Here's another example looking out over the East Atlantic. This is with the European geostationary satellite, where they have some of these spectral bands today, and they're able to look at the dry air, for example, that would come off of the Sahara Desert and mix with the developing storm, and also the larger scale flow and how it's interacting with the storm. Again, these are the kinds of capabilities we'll have in the global observing system, because not only will we have an advanced imager, as will Japan and Korea, but also so will the Europeans and the Chinese. So by the end of this decade, all the next generation geostationary satellites will have these 16-band imagers. The next instrument I wanted to point out was our geostationary lightning mapper, which is a new instrument. As I mentioned, it measures total lightning. It's about 1 meter tall. Here, another person for comparison. What I want to show you here on the lower right, with a ground-based system that detects principally just cloud-to-ground lightning, you can see features such as, here's the lightning in the eye wall, here's lightning in the rain bands. This is with Katrina coming up the coast, and there was quite a bit of lightning also over Florida. So right now we have a low Earth orbiting lightning imager. It's a NASA research mission that just recently ended. And as far as with that, you just get a snapshot. But with the continuous monitoring from GOES-R's lightning mapper, we'll be able to watch this evolution as a function of time. And we also will be able to see when there's lightning and overshooting cloud tops, for example, in the rain bands when they reach shore. We typically will see that as a favored location for embedded tornadoes that develop in the northeast quadrant of these cyclones, and that presumably will help us as well for identifying that. Shown here in the middle is from our low Earth orbiting observations we've had for the last decade. You see most of the lightning is over land, and there is lightning over the ocean, lightning over the Gulf Stream, where you have good temperature contrast. From looking at many tropical cyclones, we do see some lightning, but since we only have a brief snapshot of about 90 seconds as the satellite is passing overhead, we really don't have a good sense of how much lightning these storms may or may not produce and under what conditions. And then the last thing is we have observations from our tropical rainfall measuring mission satellite that began in the late 1990s, and by having GOES-R for the next 20 years for the Western Hemisphere, we'll now have a nice long time series. Right now it's about 17 years, so we'll go past 30 years and basically have a climate data set of lightning and thunderstorm activity over that region. This is what the data looks like. This is a movie taken from the TRMM satellite. It has a radar, a radiometer, and the lightning mapper on board. It gives us a lot of information about the vertical structure of these storms. And what's sped up here, this is just 1 minute of lightning data, but you can see lightning's identifying where the major storm cores are. And we can use this then to identify where the most developed or rapidly developing, intensifying updrafts and vertical motions are in the individual storms. And then again, I said this is just 1 minute data, and we'll be monitoring day and night the lightning activity continuously. As it turns out, in 1999 there was an F5 tornado in Moore, Oklahoma, and as the storm system moved east, there was an F3 tornado, and these are the lightning density maps. What's of interest as well is that 95% of all the lightning in these storms was in cloud, not cloud to ground, so your eyes won't see it. But the instrument's designed to see the lightning optical emissions day and night. And then lastly, there's been work with our GOES-R Proving Ground where we're demonstrating the new capabilities of forecasters at the Hurricane Center. And this is a rapid intensification index. It's a statistical model called CHIPS. And one of the things we're looking at is the occurrence on and off of where do you see the lightning, and what they find is that when you see lightning in the eye wall, that's an indication that there's stronger vertical shear in these storms, and that is an indicator perhaps that the storm won't last and the rapid intensification period will end. We have a number of training and user educational materials that we have at our gozar.gov website, and these are available if you'd like to get additional information. In terms of Katrina, and for wrap up, I just want to point out we have better batteries on the next generation satellite. During the Katrina event in our current GO satellites, we would have outages during the eclipse season, which lasts from late August to mid-October, right in the heart of the major hurricane season, when the satellite is in the Earth's shadow and we're dependent on these batteries. We won't have these types of outages with GOES-R. For monitoring storms, the increased temporal and spatial resolution of the imager will help. We have an algorithm called the Dvorak estimate that looks at the infrared features at cloud top. We have a hurricane intensity estimate algorithm that will be used in the GOES-R area, and because of the higher spatial and temporal resolution, we think that will be an improvement for monitoring intensity changes. These motion vectors I showed you will help monitor interaction with the storm environment, and as I mentioned, the lightning mapper may help us more with monitoring and anticipating intensity evolution. This would have been the case especially in the last 24 hours or so before landfall, when Katrina weakened from a Category 5 to a Category 3. And that's all I have, and thank you.
Great. Thanks a lot, Steve. That was a great oversight of all these new remote sensing products. In the interest of time, we do have to move on. If there are any questions online for Steve, please send them in. If we have time at the end, we can maybe go back. But Steve, thank you. Okay, the next presenter is Vijay Tallapragada. Vijay was the hurricane team leader and architect of the Operational Hurricane Weather Research and Forecasting Modeling System at the National Centers for Environmental Prediction's Environmental Modeling Center. Vijay is currently serving as the Hurricane Forecast Improvement Project's Development Manager, and recently he has taken charge as the Chief of the Global Modeling Branch at the National Centers for Environmental Prediction. Vijay, are you there?
Yes, I'm here.
Okay, great. Whenever you're ready, go ahead.
Yeah, can you see my screen now?
Yeah, it looks good.
All right, thank you. Thanks for this opportunity, Dan, and it's a pleasure to be part of this webinar. I wanted to acknowledge Fred Teffer, the Program Manager for HFIP, and also EMC Director Hendrik Tolman, who encouraged me to participate in this. And in this brief presentation, I would like to describe the advancements in the operational hurricane forecast guidance, particularly from the operational HFIP model that has been implemented in 2007 and ever since improved. And also go back and look at what this model would have done for those events that are of interest for us, like Hurricane Katrina. And this is an ongoing project with collaboration with NHC in looking at our current day's capabilities, how they would have dealt with these hurricanes in the past. So, as I said, the progress, you already heard from Bob Atlas on the role of HFIP, how things have improved in the past few years compared to before, and I will touch base on that again. The state-of-the-art HFIP model, it is a major collaborative community modeling effort, and I would provide some more examples on how that fed into improving our operational modeling capabilities and improving our understanding of the hurricane intensity problem and a few challenges ahead as my concluding remarks. I don't want to repeat this again, but this is the HFIP goal. We have set this baseline with a 5-year goal for track and intensity, 20% improvement in 5 years and 50% improvement in 10 years compared to a predetermined baseline came up after consulting with NHC. And the vision is to organize the hurricane community, dramatically improve the numerical guidance in this decade. So this is how it looks like. If you want, don't try to read all these boxes, but what I would like to say is there are several things going on in the community. There are a lot of organizations, universities, academic centers. They're all working on some or other aspect of the tropical cyclone research or operations. HFIP enabled all these communities to interact. And you can see EMC at the heart of the model development phase and also at the implementation phase. And there are all these partners, the GFDL, HRD, NCAR, Navy, the academic community, and the DTC, the Developmental Testbed Center. All these connections were made possible through a very organized structure. And we also extended our interactions to the international collaborations through our engagement with operational agencies in China, India, Vietnam, Taiwan, Oman, Korea, and a few other countries. And the outcome, obviously, is to reach the HFIP goals on intensity forecasts as quickly as possible. And the key to success is the community engagement and also with accelerated research to operations. That is the key for success. And just to give a brief introduction for operational HFOR, for those who don't know about it, this model as of 2015 runs in all global oceanic basins. The solid boxes represent the ocean-coupled system, and everywhere else this runs uncoupled. But essentially, all tropical cyclones throughout the globe are predicted with a very high-resolution model. This is a 2-kilometer resolution near the storm area and coupled to the ocean. Advanced assimilation of inner core aircraft data that Bob Atlas mentioned, hurricane-specific physics based on observations, and there are 3 telescopic nests, one outer domain operating at 18 kilometers, the innermost nests, the boxes here that follow the storm track are at 6 kilometers and 2 kilometers respectively. And you can see very high resolution details coming out from the model simulations. And by the way, this is Hurricane Katrina as simulated in real time. And the red line is the operational HFOR, and the black line is the observed. So the model is providing pretty rather significantly improved forecast compared to the previous versions of the model. So this is how it looks like on a busy day in the tropics. There are 6 storms here as about a couple of weeks ago. And HFOR is now running for all those storms, providing 5-day forecasts to the operational centers like NHC, the Central Pacific Hurricane Center, and the Joint Typhoon Warning Center, apart from serving NWS interests and our international partners. You have seen this slide already. On the right side is the intensity forecast errors, and the left side is the track forecast errors. This is the kind of progress that we can measure based on retrospective runs that include thousands of cases simulated by each version of these models. The purple line here is the operational HFOR that was run at 9-kilometer resolution between 2007 and 11, and a major improvement happened in 2012 when we implemented a 3-kilometer model, and then further improvements using a 2-kilometer model in 2015. So you can see a gradual decrease in track forecast errors, meeting or exceeding the 5-year goals within the 5-year period, I would say 2012 to 2015. More important is the improvements in the intensity forecast, and as Bob Atlas already mentioned, we have shown significant improvements every year using a very vast sample of hurricane seasons, sometimes including 3 to 5 years respectively. And the latest version of 2015 HFOR has shown that it was possible to meet or exceed the 5-year goals set by HFIP in terms of error. And this also reflected in the skill space from the model perspective, and we would like to really see these impacting the operational forecast from NHC as well. And as Rick Knabb mentioned, this just requires a few more active years where I think we can demonstrate the technological improvements helping operational forecast improvements. And in the busiest and the stronger typhoons in the Western Pacific, the model equally is behaving pretty good. So about 10 to 15% improvements each year since 2012. So I will quickly go back to this experiment that we did. This is a thought experiment that stemmed from discussions with NHC on how our current day models would have predicted storms of interest, including 1938 storm, 1992 Andrew, and Katrina. So for this event, I wanted to emphasize the HFOR performance for Hurricane Katrina if we were to run this 2-kilometer model then in 2005. These are the official forecasts. Each line represents a forecast issued 6 hours in sequence since its inception here near Bahamas, and then going through Florida and then entering into the Gulf. And you can see the part of the forecast that were in the long range were predicting Florida landfall compared to the New Orleans. And the track forecast errors were pretty large compared to today's forecast uncertainty as represented by Knabb. So if I have to run the 2015 HWRF for Hurricane Katrina, you can still see there is significant uncertainty in the track forecast, but certainly many of these forecasts were now trending towards Louisiana landfall, and you can also measure the improvement in terms of track errors out to 72 hours. It definitely has shown that this model would have helped address some of those track forecast errors, especially in the longer range between 48 and 72 hours. More importantly, the intensity forecasts. This storm has rapidly intensified and reached a Category 5 status, and many of the NHC official forecasts were not as aggressive as the storm intensified. And that is also reflected in our intensity forecast from official. And the HWRF forecast using the 2-kilometer model would have certainly gotten the rapid intensification phase, although there is some excessive intensification during the early stages, but reaching Category 4 most of the time, and sometimes Category 5, although there was an early landfall from the model. But in terms of error space, definitely the errors are much lower than any other dynamical model or intensity models NHC would have used for that particular event. So we went ahead and tried to probe some of those forecasts using recent tools that we developed using a 3-dimensional visualization aspects to see how the structure and the interactions with the sea surface temperatures and the warm core eddies in the Gulf. And this is an animation showing the utility of these high-resolution models in today's world and how you can interpret and utilize these for making forecasters comfortable in understanding the real-time evolution of these storms. And especially if you want to look at the impact of ocean surface here, this is an ocean-coupled run, and there is a significant cooling that follows the track of the storm, and it passes through a warm core eddy here when it was reaching a Category 5, and then passed through a cold core eddy that really decreased the intensity, and that determines the impact of air-sea interactions on the hurricane intensification. So all these tools would have been extremely useful for understanding the intensification process, and these are coming out from very high-resolution models that we can ask several questions that can be explored in terms of research as well. And here I'll show this again from a static 2D perspective. The storm is moving along with along the warm core here, and then a cold core eddy sits here before reaching the Louisiana coast. And it reminds us, again, of the critical and complex interactions between atmosphere, ocean, waves, and land, all need to be accurately represented in numerical models for improving the forecast guidance. Operational HWRF has demonstrated significant progress in improving the forecast for high-impact events like Katrina, and we will go back and look at a few more events of interest, working with NHC. And then the future efforts will continue with emphasis on high-resolution solutions for further improvements in the hurricane intensity forecasts. Moving forward, as I mentioned, the impact of air, sea, ocean, wave, and land interactions is a complex system, and we are improving our modeling systems to have a comprehensive atmosphere, land, ocean, wave, hydrology coupled system with a self-cycle data assimilation. And as Bob mentioned in his talk, the basin scale HWRF with multiple movable nests. Sorry for this animation here. This is the same animation that Bob has shown within a unified framework which is called NEMS in NOAA. And also improving our physics so that they are scale aware and stochastic that can represent the multiple scale interactions within the same HWRF domain. And eventually, the next generation global model will have the capability of these high-resolution telescopic nests that follow each and every tropical storm or convective system with a very high resolution near those regions of interest. And that would be the goal for the next generation global prediction system as well. So I'll stop here, and thanks for this opportunity.
Okay, Vijay, that was great. Thank you for the overview of some of the HWRF and HFIP activities. We do have to move along to try to stay on schedule, running a little bit behind schedule. So there was a question that just came in, but I think we'll try to hold it until the end if there's a little bit of time. So thanks, Vijay, and I'm sorry we can't linger on you right at the moment, but hopefully we can come back around at the end.
Sure, no problem.
So we're going to switch gears a little bit now and hear from Jeff Payne, and he's going to talk a little bit about coastal resilience and decision support tools. And I'm going to switch control over to his computer. And Dr. Payne is the acting director of NOAA's Office for Coastal Management. This office's mission is to ensure healthy coastal ecosystems, resilient coastal communities, and sustainable coastal economies. Jeff, are you on the line?
Sure, and thanks, Dan. I appreciate the introduction, and good afternoon, everyone. So my remarks are going to shift a bit from what we've been hearing to look at the importance of risk communication and the role of social science and technology. And I'll begin by saying that if nature is any kind of teacher, we've actually learned a lot over the last 10 years, not in a unique way, but maybe in a relatively dramatic way. Whether it's wildfires or tornadoes, droughts, hurricanes, or flooding, we've had some really good instructors. And as a result, I think that people are talking more about how we might better prepare. And I feel like Katrina was a galvanizing moment that kind of started that conversation. And if anything, Sandy has really nailed it down. So I like to think that there are two truisms in life amongst many. And one of those is that many of us tend to underestimate risk, both personally as well as in the way in which we work within communities. And the second is that the time to prepare is before a tragedy actually happens, so that we are doing that kind of thing when the skies are blue. So I want to address some of the ways that we see coastal communities in particular are starting to make progress, and especially getting citizens involved. And along this path, NOAA is working with communities to increase public understanding and hopefully to change the way people actually think about risk. So risk is really all about the likelihood of an event and the consequences. For example, if the probability of an event and the consequence are both high, like a hurricane here in my hometown of Charleston, South Carolina, I'll want to actively reduce my risk. If the event is rare and the consequences are minor, for example, maybe snowfall in Florida, my risk tolerance is likely to be greater. But the point here is that we manage our risk based on what we know and what we may expect and what we are willing to accept in terms of consequences. The unfortunate part of this is that Mother Nature is showing us that probability is not always on our side, and that future impacts of a changing climate are going to introduce even more uncertainty. So since we can't change the frequency or severity of a storm event, for example, we have to change essentially how we learn and how we prepare, respond, and indeed recover from events. Many of NOAA's efforts over the past 10 years and our priorities for the future have to do with helping communities better understand and communicate risk and vulnerability. So Katrina reminded us of what a hurricane can do. Other storms, Rita, Irene, Sandy, Wilma, they've all brought home the same painful lesson to communities. And as a result, more people are looking at their risk and vulnerability and figuring out ways to make their communities more resilient. NOAA is helping by providing a suite of tools and services to quantify and communicate risk. And we are seeking to marry, for example, social science information and technology to make what can be oftentimes complex data much more useful, usable, and impactful. When people better understand and can even visualize their risk and vulnerability, they're capable of making, I think, better decisions. So in the next couple of slides, I want to show some risk and communication applications and the role of social science. Social science helps us understand why people do what they do, such as why some evacuate from a storm and others don't. It's a way to look at the people side of risk. Why are some populations more vulnerable? Why are some populations more resilient? This slide profiles the Coastal Resilience Index. What this does is provide a simple, very inexpensive method for community leaders to perform a self-assessment of their community's resilience to coastal hazards. With Sea Grant and NOAA trainers at the helm, community members have been able to gather together and identify community strengths and weaknesses and how they want to address the weaknesses prior to the next hazard event. It basically guides discussion within a community and promotes engagement. This effort began with Mississippi, Alabama Sea Grant and NOAA in 2010. 52 communities so far have participated, and that number is actually growing. This next slide shows an outreach, climate outreach community of practice. And part of the success of the Coastal Resilience Index that I just showed you has to do with the social science principle that recognizes the power of bringing people together. This example comes from the Gulf, and again with the Sea Grant and NOAA community working together. 5 years after Katrina, the NOAA Gulf of Mexico team and Sea Grant programs established a community of practice, and that's a volunteer network of outreach and education professionals and community officials who started working together to do a couple of things. They're looking at exploring the state of climate science in the Gulf region, learning how coastal communities can adapt to climate change impacts, and sharing lessons learned and developing common messages for communicating about climate. This group holds free webinars to provide access to experts and meets to share challenges and experiences, which enables sustainable learning. Next, I'm going to show you a snippet of what we call a quick draw animation, and it's designed to educate on the hazard of storm surge. So social science tells us, the research tells us, that many people don't understand really what storm surge is and how devastating it can be. So what we've done is worked with the Weather Service and the National Hurricane Center to bring hazard information to the public in a fresh format, and this is one of the things that we have actually recently completed in collaboration within NOAA. So here we go. I'm going to play it, and it's just a very short snippet.
Not limited to coastal properties, storm surges from seawater traveling up streams and rivers can flood inland homes too. And is it strong? Able to carry away cars and demolish entire communities.
So basically, we want people to get information when the skies are blue. I mentioned that earlier, before disaster strikes, and this helps us to save lives and to reduce the impacts on property. If you Google Storm Surge Fast Draw, that's the title, Storm Surge Fast Draw, you can watch the whole video. It actually lasts about 90 seconds, and it's an incredibly, I think, effective educational tool, which is at a level that anyone, including children, can actually understand. So this is what makes risk communication tools so useful. In those, we're able to convey complex ideas in a format that can be viewed and shared broadly. And we are seeking to reach new and larger audiences with a very strong and important message. So I want to switch in these last couple of slides to what we call decision support tools. You may have heard about NOAA's Digital Coast. It's a data and tool delivery system, basically a web portal with data, tools, trainings, and services that communities can use to increase their understanding of risk and enhance community resilience. And many of our Digital Coast resources incorporate social science with technology to communicate risk. The first example here is our coastal county snapshots. And with this tool, what users do is select a county of interest, and the tool turns complex information into an easy-to-understand handout, complete with charts and graphs. Topics, for example, include flooding, wetlands benefits, and statistics about ocean-based jobs and the economy. Each snapshot contains information about steps communities can also take for using the information. This one in particular on the slide is the flood exposure snapshot, and it provides local officials with a quick look at a county's demographics, its infrastructure at risk, and environment in the flood zone. And the way this is being used, for example, in Mississippi and Louisiana, the Red Cross is using this information, this tool, to help develop hazard preparedness and recovery plans to assist especially vulnerable communities in their area of jurisdiction. So with flooding, whether it's from sea level rise or tides and waves or a coastal storm, the first question that people usually ask is, how will my community be affected? And the tools developed by NOAA are being used by communities to help citizens see the possibilities and to formulate really what need to be realistic preparation, response, and recovery plans. This slide shows our coastal flood exposure mapper. The geography here is basically from Gulfport to past Biloxi in the Gulf. And with this tool, what users can do is pick a location and create maps that show which areas are at a high risk to flooding. It enables us to undertake composite mapping across multiple flood hazards, for example, storm surge and shallow coastal flooding and sea level rise. But as I noted earlier, people underestimating risk represents one of our biggest challenges. So in this case, when the data through this kind of tool and display is made visual, the potential consequences become much more real, more tangible, and people, I believe, tend to pay more attention. So these maps offer a good way for communities to get the resilience conversation started. And the last slide here is the sea level rise tool for Sandy recovery. Many of you may have heard about that, especially if you live in the Northeast, New York or New Jersey, for example. This is another approach that involves incorporating sea level rise projections, in this case, on top of the Federal Emergency Management Agency's advisory-based flood elevation data. And the FEMA maps basically only account for flood risk based on current conditions. This is really a future risk planning tool. So in order to address future risk, including the impacts of sea level rise, an interagency and state partnership formed following Sandy and created this particular tool, the Sea Level Rise Planning Tool for Recovery. It's a proactive tool. It uses best available science and data, and it takes into account future risk to help communities make better long-term decisions about how and where to rebuild or where to start new development, and has been utilized, I think, quite effectively in the Sandy recovery area in the Northeast. So, last slide, last set of comments. I hope you see from what I've talked about that NOAA and its partners are helping to provide the information communities need to better understand risk and vulnerability through social science and technology applications. There's an old saying that climate is what you expect and weather is what you get. And I know that we are seeing today changes in our environment. One of the most tangible, for example, being the increased frequency of sunny day coastal flooding, what we call nuisance or recurring flooding. And that's due to sea level rise and or subsidence along portions of especially our East Coast. Does the public understand what this is and what it means in terms of risk and the decisions we need to make to reduce our vulnerability? That's the question. So our increasing role now is to help communities better define their risk using data and social science and technology, and to collectively determine the best set of strategies to increase their resilience to a range of hazards, both episodic, like hurricanes, we've been talking a lot about today, as well as those that are chronic, for example, climate change. So Dan, back to you.
Great, thanks a lot, Jeff. Again, unfortunately, we have to keep moving along, so I have received a couple questions by chat, and hopefully we can get to those at the end. If anyone has a question for Jeff, please do send it to me by chat. But in the meantime, Jeff, thank you so much for the presentation. That was great. Okay, next up is Tom Knutson. And I have transferred control over to Tom's computer. Tom is the head of the Climate Impacts and Extremes Group at NOAA's Geophysical Fluid Dynamics Laboratory, and his research interests include hurricanes and climate, as well as climate change detection and attribution. This talk and the next talk, we're heading back a little bit in the direction of more modeling results and efforts, as well as from looking at that from a climate perspective. So Tom, are you on the line?
Yes, I am.
Hi, Tom. Whenever you're ready, we can see your slides, so go ahead.
Okay, great. Yes, so I'm going to spend just a few minutes covering some of the highlights of progress made over the past 10 years since Katrina in hurricane modeling and prediction across timescales at GFDL. And by that, by across timescales, I mean everything from short-term hurricane prediction out to looking at possible changes in hurricane activity due to climate change. And this work that I'm describing has a large number of contributors, some of whom are listed on the screen here, and many more contributors not listed. So I want to start with looking at Hurricane Katrina and the GFDL Hurricane Prediction Model, which is an operational hurricane prediction model run operationally at the Weather Service since 1995. This is an animation of Hurricane Katrina in forecast mode. This is a version of the model which includes some loop current features which were not in the model at the time of Hurricane Katrina. And you see what happened, as Vijay mentioned earlier, Hurricane Katrina ran over a warm core ring and intensified rapidly there in the mid part of the Gulf before generating more of this cold wake as it encountered after it passed over the warm core ring feature. So this is an example of some new physics that we now have in the GFDL hurricane model, which enables us to more realistically simulate a hurricane and its interaction with the ocean. Now, if we look at the performance over time of the GFDL hurricane model in terms of intensity prediction, that's this red line here. So this is looking back from the year 2000 through 2014, the average intensity forecast error from the model. We see a quite substantial improvement showing up in the models, in the GFDL hurricane models, intensity forecast errors. Now, as has been mentioned earlier today, it's a little early to say whether this represents the true level of improvement, because this is a relatively short record to look over, and also some of the recent seasons may have been easier ones for intensity prediction than some of the earlier seasons. But we're at least cautiously optimistic that we're headed in the right direction and showing some improvement in the models for these intensity predictions. Now, this same model, the GFDL hurricane model, we also have used for climate simulation of hurricanes. And for this, we basically simulate hurricane activity in the Atlantic Basin for present-day conditions, and then for late 21st century conditions as projected by the CMIP-5 multi-model ensemble of climate models for the late 21st century, which is basically a warmer climate condition by the late 21st century. So the top image here shows the present-day simulation of Category 4 and 5 hurricanes over a 27-year sample using our model. And again, we're downscaling storms that we simulate in a coarser resolution model. We downscale them into the GFDL hurricane model as individual storm cases. And in doing that, we're actually able to simulate intensities as high as Category 4 and 5 intensity. We see, if we count these, then that under warmer climate conditions, we're simulating about 40% more Category 4 or 5 hurricanes than under the present-day conditions. So a brief summary of these types of projections: we're tending to simulate fewer hurricanes overall in the Atlantic under warmer climate conditions, but slightly stronger hurricanes and more of the most intense variety of hurricanes and higher rainfall rates. But this is just an example of what we mean by cross-time scale, looking at hurricanes across time scale. Now, looking at the seasonal prediction of tropical storm activity, we've made great strides in the past 10 years at GFDL, work led by Gabe Becky. This figure here is showing where GFDL seasonal prediction, global seasonal prediction model, has skill at simulating, or rather at forecasting tropical storm activity from July 1st initial conditions. So this is retrospective skills, so we look back over time at a lot of different years. And the orange and yellow areas are where regionally this model has predictive skill at simulating either more active or less active tropical storm activity conditions for the coming season. So this is new information, wasn't available at the time of Katrina, and demonstrates these new developments with modeling at GFDL. Now, other modeling work at GFDL by S.J. Lynn and Lucas Harris has been focused on building even better dynamical cores and systems of models which can use techniques like stretching and nesting to focus resolution in on certain parts of the domain. So here we see a global model where through a combination of stretching and nesting, the model's telescoping in on the central planes and putting more of the model's resolution there where it's needed. And we can see in this next image an advantage of going to much higher resolution. This is in this highest resolution part of the domain where you're getting down to, say, just a couple of kilometer resolution, horizontal resolution. The model can begin to simulate these tornado-like vortices within supercell storms. So we think this is really the future of cross-timescale modeling, here showing how a global model, we can embed this high-resolution domains and then study these these severe weather events like tornadoes. Now, getting back to hurricanes, the latest version of the GFDL forecast model for seasonal tropical cyclone predictions is now running at 25-kilometer grid spacing and is actually able to simulate Category 3 through 5 hurricanes with no further downscaling. So this is a full global coupled model that we're showing here. And the top image is showing the tracks over a couple of decades from the model. This is the so-called high floor model. And the bottom is the observed the observed tracks. And we see the model has a very realistic simulation of where the tropical cyclones are occurring, as well as a realistic depiction of where the most intense storms are occurring. The color coding there is indicating the Saffir-Simpson category, with the red tracks being the Category 5. Now, this same model can be used to simulate the year-to-year variability of Category 4 and 5 systems in the Atlantic Basin. If you restore this model toward observed sea surface temperatures and run it over a few decades, that's shown by this right panel here. So the black curve is the observed year-to-year variability in the Atlantic of the number of Category 4 and 5 hurricanes, and the red curve is what we get using the high floor model with a large ensemble, was shown by the shading. But you see that the ensemble mean from the high floor is reproducing the observations rather well with a correlation of 0.63. So we think this is remarkable progress at being able to simulate this year-to-year variability. So encouraged by that, then Gabe has begun then looking at the predictability of Category 3 through 5 hurricanes in the Atlantic from July 1st initial conditions, and this is showing the retrospective forecast skill of the coming season of the number of Category 3 through 5 hurricanes in the Atlantic Basin, here run in retrospective mode. So we see the black is the observed number of Category 3 through 5 major hurricanes in the Atlantic, and the green is the ensemble mean of the forecast from the model beginning from July 1st initial conditions. So again, the model showing remarkable ability to simulate the year-to-year variability of these intense hurricane systems. The gray shading here is showing the spread amongst the ensemble members. Now, they've actually run it for 2015. I'm not showing that here, but the 2015 forecast from the model has been provided as guidance to NOAA's seasonal hurricane outlook team. So this is, again, new and exciting stuff. And I just want to show now an animation of this high floor model that's showing this, that's producing these Category 3 through 5 hurricanes. So this is a global simulation with this model using observed sea surface temperatures. So this is more of a climate simulation, not a forecast. But it's just showing the development of tropical cyclones in the various basins of the globe. We see some going now in the West Pacific Basin, the typhoons, and the tropical cyclones are identified by the little colored rings, and the color of the ring signifies the intensities of the storms. So we'll see here in a moment some a little bit of activity starting in the Atlantic basin. As you see, one of these easterly waves coming off, it's reversing across the Atlantic basin, and here's another one following it, and these storms are beginning to intensify into hurricanes. So it's a very beautiful simulation of showing all the different scales of activity, including the cyclones, the tropical cyclones. So this is what we think is the future of seasonal prediction coming through with the GFDL high floor model. And so with that, I'll just wrap up to summarize that NOAA and GFDL has been engaged in extensive numerical model development and research toward a predictive understanding of hurricane activity on timescales ranging from hours out to centuries. And our focus has been on connecting fundamental research with improvements in predictive capability. So I've tried to highlight some of those in this brief talk, and now I'd be happy to answer any questions. Thanks.
That's great. Thank you, Tom. Unfortunately, I don't think we have time to go to questions right now. Again, I'll remind people online, send a chat message if you'd like to. Maybe we can try to have a Q&A session at the end. I do want to mention for everyone online that the sluggishness of the videos is WebEx. These animations actually are very streamlined, and there's a lot more, the frame rate is a lot finer in reality than what you're seeing on WebEx. So we're going to post these slides online, and you can download them later if you'd like to see the animations with a little bit less of that latency. Okay, so thanks a lot, Tom. Next speaker is Jim Cosson. And Jim, I'm transferring control over to your computer. Jim is a meteorologist in NOAA's Center for Weather and Climate in the National Centers for Environmental Information. He specializes in tropical cyclone research. Jim, are you there?
Yes, I am. Can you see my first slide?
Yeah, it looks great, and you're coming through clear on the phone. So whenever you're ready, go ahead.
Perfect. Okay, hello, everybody. This is a slightly different talk than the ones that we've been listening to. This would be probably categorized more in the area of some of the more recent advances in terms of our understanding of how tropical cyclones are responding to climate variability and change. My collaborators on this work have been Kerry Emanuel at MIT, Gabe Vecchi over at GFDL, and Susanna Camargo at Columbia. And this is the slides I'll be showing today are based on a couple of papers, one that was published last year and one that's in preparation. Tom touched on this briefly in his talk just before mine, how tropical cyclones respond to climate change. And there's a lot of progress that's been made, certainly since Katrina. And I think the IPCC AR5 and the U.S. National Climate Assessment combined give a pretty good idea of where those advances have taken place. We do have a sort of a general expectation based on our theory and the modeling studies that have been done that the effect of climate change on tropical cyclones is going to depend a lot on the specifics of the patterns of the forcing and the mechanisms behind the forcing. For example, if sea surface temperature changes just due to warming through greenhouse gases, you'll get a different response than if sea surface temperature is also affected by, say, a reduction of the trade winds. So there's a lot of very fundamental theoretical understanding that's been promulgated since Katrina in this area. For intensity, Tom touched on this. We might expect some small increases in mean intensity, but there is the potential for large increases in the strongest storms, and Tom showed an increase in the Atlantic, for example, of Category 4 or 5 storms in the next century. Frequency, there's a general consensus that we don't expect any change or even possibly a decrease, and that's due to a mid-level saturation deficit changes and genesis inhibition. But there's a lot of regional uncertainty in all of this. What I'm going to talk about today, though, is more related to track changes, and this is also an extremely important metric to consider because it's certainly, in terms of coastal impacts, small changes in track, even all other things being equal, can certainly lead to large changes in coastal impacts and landfall. So this is kind of a summary of our paper from last year. We looked at where tropical cyclones globally were achieving their lifetime peak intensity, and we looked at the latitude where they're achieving that lifetime peak intensity, and we looked at just annual time series, and we found a very robust trend that stood up to reanalysis and was statistically significant. And basically, we're seeing about a half a degree of poleward migration in the northern hemisphere and a half a degree of poleward migration in the southern hemisphere, combining into about a degree per decade of global expansion, if you think of it as sort of interhemispheric span. And one of the more intriguing things about this result was that the variability and the rate of expansion are very consistent with the completely independently observed and documented expansion of the tropics via expansion of, say, the Hadley circulation in both the northern and southern hemispheres. So in a way, our paper sort of intimated an indirect attribution that, tropical expansion has been linked and attributed to greenhouse gas and aerosol forcing, and we seem to have this independent response by tropical cyclones to it that's behaving very similarly. And that's about as far as we were able to take it. The signal itself varies quite a bit by region. So this is just kind of an overview of, and again, limited data that we have access to. Sometimes the data doesn't go back very far, and it's difficult to say much. But we have substantial poleward trends in the southern Indian Ocean, and this has been confirmed by forecasters that operate out of La Reunion, and they've communicated with me and said they've done their own reanalysis, and they've confirmed this to be real, at least within the limitations of their reanalysis. We also find a very substantial poleward trend. By the way, I should have mentioned this before, but if you haven't noticed, the numbers on the ordinate are increasing downwards in the southern hemisphere and increasing upwards in the northern. So these are all poleward trends that we're seeing. Large trend in Wellington, not much trend in the Atlantic, and in fact, if we limit this to storms that are 35 knots or greater, we actually have an equatorward trend here. And so the Atlantic is most certainly behaving differently, and as seems to be the case for just about every metric we look at, it's been behaving sort of marching to its own drumbeat. And a lot of that could be due to the regional aspects of either internal variability like the AMO, as Gerry talked about, or external variability from aerosol forcing. Not much trend in the Eastern Pacific or the Central Pacific, but all four sources that we have, these are best track data sources in the Western North Pacific, all have a robust poleward trend, and this is particularly robust over lots of different reanalyses. So I'm going to just focus on the Western North Pacific for the remainder of this talk. Over here, this is now strictly the Western North Pacific. The panel F is really just an ensemble of those four data sources we just looked at the previous slide. So again, you have an average of about 0.55 degrees of poleward migration per decade. And this shows a little bit more information. This is the change in distribution of latitude, and the latitude showing here on the top here. This is the phi LMI is the latitude of LMI. So for all the different storms, we have this shifting of the distribution. So what we did that's new here with Carrie Manuel and Susanna Camargo is to now look at how the models might capture this. And there has been previous work done that have looked at track changes in the Western North Pacific using models. We're taking a slightly different angle here, but particularly in comparison to the observations. But the first thing that we wanted to do was see how the CMIP-5 simulated tropical cyclones behave in the historical runs. So this could be roughly compared to this, even though the periods are slightly different. And what we find is that the CMIP-5 historical runs tend to underestimate this poleward migration, and you can also see this here in the time series of the annual mean. And that's very possibly because of the fact that the fairly well documented bias in the CMIP-5 models, that they don't capture the observed poleward expansion very well. if we now project this into the next century, the poleward expansion does become significant again, and this shows the general change in the distribution. It's a shift and a shape change, and this shows the time series. And again, we have a statistically significant migration. Now, the other thing that we're doing here is we're downscaling from either reanalysis or from the CMIP-5 model output, and we're using Kerry Emanuel's method for doing that. So now if we go back and downscale from reanalysis, we see a pronounced poleward migration. That's the time series shown here. That's very consistent with the observed. And then when we project that using CMIP-5 model output into the next century, again, we find a significant poleward migration, and again, smaller in amplitude. And we're not 100% sure why this is true. We're looking at it now, but again, it's if indeed the expansion of the Hadley circulation is a major player in causing this behavior in the tropical cyclones, then this low rate might be actually larger in reality than what we're seeing, because the models don't seem to capture that very well. The upshot of all this is summarized in this figure, so I'll spend a couple of minutes on this. These are regional changes in tropical cyclone exposure as measured by track density. The values here are basically the number of days per year that a tropical cyclone is residing in this 2 degree by 2 degree box. And so this is the observations, the first 17 years of good observations, 1980 to 1996, and this just shows the climatology during that period of track density. Now this shows it during the latter half of that period, and this shows the difference. And over here, this fourth panel D shows the regions where these differences are significant at 90%. So in general, then, what we are seeing is a pretty clear reduction in tropical cyclone exposure throughout this large region here, which encompasses the Marianas and the Philippines. And also what we are seeing is an increase in tropical cyclone exposure throughout this region of the Ryukyu Islands and Japan, and a little bit on Taiwan as well. So this is actually there is a reduction in overall basin-wide tropical cyclone frequency between these two periods. So the poleward shift here is actually large enough to dominate over the basin-wide decrease in frequency, and we still get increases in exposure in these regions. And they are statistically significant, at least at 90% in a number of these regions. Now, if we go ahead and look at the CMIP-5 simulated storms projected out to 2099, and we do a similar composite analysis, the first 30 years versus the last 30 years of the simulation, we see a remarkably similar change. So the overall track density in the first and second, and the difference between them, once again, we see a reduction of exposure throughout this region, and certainly concentrated in the region of the Marianas and the Philippines. And again, we see an increase in the region of Japan and Korea and the East China Sea, as opposed to a decrease in the South China Sea. So this is really quite a remarkable change, and in fact, there are regions down in the area of the Marianas and Philippines where the TC exposure is cut roughly in half, and there's regions here around Japan where the exposure has roughly doubled. So to summarize this, and I want to particularly look at point 3 here, but basically, the one takeaway would be that this is an important metric to consider. Track does respond to climate variability. It does seem to respond to climate change, and this can really have very substantial effects on exposure and human mortality risk. In the western North Pacific, we've definitely seen or we've observed in the past large and significant changes in tropical cyclone exposure, and the CMEP5 models do project this behavior to continue in a very similar pattern and rate under the business as usual emissions projection of the RCP 8.5. Point 3, I think, is a particularly important one, and that is that this sort of shift may appear like a very positive thing for some regions, but the give and the take of it is not balanced. The regions such as in the Marianas don't have a lot of vulnerability. They have very high resilience. They build homes like concrete bunkers, whereas Japan is very, very exposed and going to be very vulnerable to this sort of change. And so you get a sort of a compounding factor here. And so the final thing I'll leave you with is that we are trying to understand better what exactly the attribution should be here. Is it really Hadley circulation expansion? Could it also be that the models tend to project a permanent El Nino and the storms are responding to that? And that's a work in progress that we're working on, and I'll leave you with that. Thank you.
Great. Thanks so much, Jim. We're going to move along to our final speaker, who's Mel Landry. And Mel is a marine habitat resource specialist with the NOAA Restoration Center in Baton Rouge, Louisiana, where he is NOAA's technical Deepwater Horizon Restoration in Louisiana, as well as a project manager for projects implemented through the Coastal Wetlands Planning, Protection, and Restoration Act. So we're going to be switching topics a bit here, talking a little bit about physical coastline issues related to Hurricane Katrina and hurricanes. Mel, are you on the line? Mel, are you there? We can't hear you at the moment.
There we go. How about now?
Great, yes.
All right. So thank you very much, Dan. And as you said, I'm Mel Landry with NOAA Restoration Center, and we'll have a bit of a change in direction here. I'm going to take a look at one way NOAA is working to reduce risk to communities in an area of operations where our mission to understand climate and weather intersects with our mission to conserve and manage coastal ecosystems and resources, which is pretty neat that those things can intersect. I'm going to do that by introducing you to the habitat restoration work NOAA and our partners have conducted in coastal Louisiana since Hurricane Katrina, with a focus on the barrier islands of the Barataria Basin. So before striking the coastal communities of Louisiana, Mississippi, and Alabama, Katrina swept over Louisiana's vast coastal wetland complex. Over 40 miles of forested wetlands, marsh, and barrier islands once buffered the New Orleans metropolitan area and the surrounding communities from the Gulf of Mexico to the south. But since 1932, over 1,800 square miles of this buffer has been lost. That's roughly equivalent to the land area of the state of Delaware. A 1963 Army Corps of Engineers report set the rule of thumb that 2.7 miles of wetlands can reduce storm surge by a foot. Today, we know that can vary widely depending on the size and intensity of the storm, but we generally agree that coastal wetlands can play a key role in helping to reduce the impacts of storm surge. Recognizing the importance of that role that habitat plays in storm surge risk reduction, the Louisiana legislature directed the Coastal Resource Management Community, led by the state of Louisiana, to develop the 2007 Louisiana Coastal Master Plan, which was updated in 2012 and will continue to be updated every 5 years. NOAA took a lead role in designing and constructing restoration of Louisiana's barrier islands with a particular focus on the islands of the Barataria Basin. Funding for NOAA-led projects was provided largely by the Coastal Wetlands Planning, Protection, and Restoration Act, or QWPRA. Louisiana's barrier islands are the remnants of former deltas of the Mississippi River that have been reworked by wind and waves. Each of these blobs of color here represents an abandoned delta or the current delta in the bottom right case of the Mississippi River as it changed deltas and swung across lower Louisiana. As the abandoned delta subsided, barrier islands became detached from the mainland by lakes and bays. These islands exist as natural habitat for the most part, with limited or no road access and minimal human impact. These are not the amenity beaches of our neighbors in the Florida Panhandle. In addition to serving as the first line of defense against the effects of hurricanes, they also serve as a valuable habitat for resident and migratory species. As one example, as recently as 150 years ago, the islands of Ile-de-Nere and the Terrebonne Basin were attached to the mainland, and stories from earlier times noted a horse could be ridden to the island. The Great Storm of 1856, also known as the Last Island Hurricane, severed Ile-de-Nere in two and removed any remaining connection to the mainland. This is the fate of Louisiana's barrier islands. As inland wetlands are lost, they become more isolated. Larger volumes of water move through their passes with each tidal cycle, further eroding their banks. Waves spread their sands across bays and sounds, and eventually they sink below the water, no longer to serve as a buffer to storm surge or as habitat to fish, birds, or mammals. But that doesn't have to be the end of their story. Beaches, dunes, and marsh habitat can be rebuilt by harvesting sediment from offshore or even from renewable sources in the Mississippi River. This gives you a sense of the scale of work we do. These are very large pieces of equipment, bulldozers and excavators in front of you, and the work that on this particular barrier island stretches as far as this picture can see. Without the presence of human development, such as condominiums or homes, we're able to recreate the entire continuum of habitat from the beaches of the Gulf, which would be on the right side in these design drawings, to the intertidal marshes of the bay on the left. Sand and mud for beaches and marsh, respectively, is harvested using a hydraulic cutter suction dredge and pumped up to dozens of miles where it is shaped into new habitat where barrier islands once existed. Since 2005, NOAA and our partners have restored nearly every island in the Barataria Basin. With 2 of the 3 remaining islands scheduled to go to construction this fall, we've given new life to this important structural component of the coastal ecosystem. Here we see the restoration of 2 adjacent islands, Shell Island East on the left and Pelican Island on the right. In 2010, sand berms were placed on the toe of the islands in response to the BP oil spill. By 2012, Pelican Island on the right had been completed, the restoration that is, by NOAA. And today its neighbor to the west, Shell Island East, has been given new life through a project implemented by Louisiana's Coastal Protection and Restoration Authority. This island on the left-hand side, Shell Island East, will continue to the west under a natural resource damage assessment project funded through BP oil spill early restoration funds. We've also observed the way these new islands react to hurricanes. In 2012, Hurricane Isaac made landfall while two of our barrier island projects were under construction. The eye of the storm passed directly over West Bell Pass Barrier Island Restoration Project. The work on the beach of West Bell was nearly complete, but creation of the marsh apron behind the island had not yet begun. The storm washed that sandy beach material into the open water behind it, forming breaches in the beach and the containment dike for the marsh platform that you see on the lower left side of the picture. In contrast to West Bell on Pelican Island, the marsh platform was built first before the beach. When Hurricane Isaac made landfall, the beach experienced overwash, but because that marsh platform, even unvegetated, was in place to capture the moving sand, no breach occurred on the beach or bay sides of the island. Lessons like this help us to modify our construction sequence, leading to more resilient islands that can survive storms during and long after construction. Over 36 miles of barrier shoreline have been restored in the Barataria Basin alone, with over 4 more miles scheduled for construction in the next year. In all, 9.6 million cubic yards of material will be used, enough to fill the Louisiana Superdome 7 times. Capitalizing on habitats to support coastal resilience is a lesson we're carrying across the nation. In May, NOAA requested proposals for a grant program for habitat restoration specifically focused on building communities more resilient to risk, such as tropical cyclones and sea level rise. By capitalizing on natural defenses as part of a multifaceted approach to protecting communities, we can build a more sustainable working coast, supportive of the needs of human and non-human inhabitants alike. And that concludes my presentation. I can hand it back to you, Dan. Hopefully we have some time for questions for myself and other presenters.
Yeah, thanks a lot, Mel. That was really fascinating look at the hands-on work that NOAA is doing in the Gulf. So thanks for providing that perspective. If there are questions for Mel, please send them in. If there are any questions for any of the other speakers, I believe we still have Bob Atlas, Jerry Bell, Jim Cosson, Jeff Payne, Rick Knabb and Tom Knutson on the line, so feel free to send in a couple. I will go back earlier. There was one question for Rick. It looks like Rick may be off the phone at this point. Rick, are you there? I see Rick's still on the WebEx, but I think he might have lost the audio connection at this point. There was also a raised hand from the AOML conference room, so I'm going to unmute their line and just see if there's a question down at AOML. Are you guys there? Questions are kind of coming from every angle here in WebEx. Okay, I'm not hearing anything from AOML. You can send me a chat message if there was a question down there. There was a question from Jenny Stiletovich about GOES-R, when GOES-R will launch. Unfortunately, Steve had to step out for a flight a little bit early, so he's no longer on the line, but we can connect you by email, and he can try to answer that question for you. I'm sorry we can't handle it right now. And
Can I ask Tom a question?
Yeah, sure. Tom, are you on the line?
Yes.
Hi, Tom. Seth has a question for you here in the room.
Hey, Tom. It's Seth at AAP. Just to look at, maybe Jim might want to jump in also, looking at, at the models with climate change. Does that factor in, negative AMO period, cooler AMO periods, or does it see a change in the AMO, or is it? Or does the Atlantic just you pull the Atlantic out and it doesn't really count?
Well, for the future projections that I showed, we were not really accounting for the AMO. We just view that as noise in the system, and we were looking for the forced signal due to the changes in greenhouse gases and other forcings. But the AMO is actually a sizable, the multi-decadal variability in the Atlantic Basin is a sizable noise signal, whether it's due to internal variability or radiative forcing. And in one of our earlier papers, we indicated that it may take a number of decades before we would actually be able to detect the type of climate changes that we're simulating in our projections. The reason why it would take so long to detect it is because of the relatively large multi-decadal variability in the Atlantic. But no, we're not really including it explicitly in these projections.
Thank you.
And Mel, there was a question for you. Are you still on the line?
I am here.
Okay, this is from Mark Schleifstein, and he said, he asked what plans are in place for adding sand sediments to islands as the new work erodes over time, particularly in the context of the 20-year project lifetimes?
The way these projects are designed is they're actually designed for that 20-year life, so they're front-loaded with the amount of sand material necessary for the islands to survive that lifetime. Now, certainly we understand that this is a dynamic system, and these things will not exist into perpetuity without additional support. We do not have plans necessarily to go back to these islands past their project life, but as the plan for the management of coastal Louisiana is refined every 5 years, we will certainly be looking at past areas to see if those are places we need to focus additional resources to go back in and help sustain or rebuild again something that might have been lost unplanned.
Okay, great. Thanks a lot, Mel. So I think we're a little bit over time now, so we should wrap up. I want to very sincerely thank all of the speakers for taking the time to present today and also putting up with my harassment over the last couple of weeks to prepare for the webinar. I think this is a very interesting webinar with showed the broad array of work that NOAA is doing related to hurricanes. We hope that this has been very informative for the audience, and I also appreciate everyone logging onto WebEx and those who came here in the room. We're going to make the slides and the recording of this webinar available on the website hopefully within the next day or so, and you can find the website link in the invite email that's been circulated. If you have any questions or don't have the link, feel free to email me. My email address is daniel.barry, and that's B-A-R-R-I-E, @noaa.gov. So again, thanks everybody for joining. Take care.
Thank you for doing this.
Thank you, Dan.